bound on how long this algorithm might take given n steps. So big O itself is a formal.
So this is where we really start to make things formal in the class, and we introduce asymptotic notation, like big O, omega, and a little bit of theta as well. And I think it's helpful to give students this vocabulary with which to start to talk about the running times of algorithms.
I have to say, when I've taught section in the past, I feel like this is a really tricky topic to teach because it gets mathematical, and I feel like people's eyes can just totally glaze.
It is, and so this is why we don't spend a huge amount of time on the formal definition of each of these, where you really capture the constant factor and the definition of big O and omega, and especially in years past. I think in 2007, maybe '08 or give or take, I actually gave the formal definition of all these, and it just felt too much detail. And I think we've benefited from a more intuitive appreciation for what these is, for what each of these is. And even then, I mean, I've done a couple of angles here, right? We did a bit of the math where we show what the recurrence would end up being mathematically and how you can then factor everything out, and you can actually see the higher order terms, the lower order terms, and then start striking them. And I've never felt super comfortable with how we go about striking those higher order terms until I gave a proof by example, which was certainly not a proof, but when we do the example of like if n is 1,000,000, and you really start to see that like 1,000,000 squared minus 1,000,000 divided by 2 is really so close, it seems, to just 1,000,000 squared.
Right.
And so that, with that example, with that proof by example, so to speak, or I think, am I really trying to get students to appreciate or just kind of like accept like, okay, yeah, it's not really a big deal once asymptotically n is approaching a really, really, really big number as we present.
It's tricky though to teach, I think, to broach this topic in an intro class. Like this is there are classes at Harvard here where you can spend an entire semester learning about big O notation.
For sure. But to be fair, I mean, we use it at a fairly simple level, right? I mean, we define it formally as big O is an upper bound, omega is a lower bound, and theta when they're one and the same. But we also take the liberty of generally only describing the cases to which these are interesting to us. So we almost always use big O, if not always use big O, to talk about really worst case running times. But you can use big O to talk, of course, about like average case running time, best case running time, and any number of other cases. But for us, it's the intuition of like applying an upper bound to the worst case and conversely applying a lower bound to the best case that allows us to have, I think, a pretty reasonable, pretty accessible discussion that's still useful too when it comes to the analysis of some of the algorithms we could look like.
Yeah, it allows us to explain things like why bubble sort can be faster or what that short circuiting could mean or translate to. Numerically.
And I think a higher level class to which we ultimately defer can go into the nuances of average case versus best case, worst case, amortized case, and so forth.
Right.
And that's perhaps where that level of nuancing belongs.